Hi folks, in this video we're going to have a look at a question involving standing waves in an air column. So for this question we have a loudspeaker which is connected to a signal generator and that's placed close to the open end of a resonance tube closed at the opposite end. The frequency of the signal generator is increased until the first position of resonance is obtained. So we're first being asked, how would the experimentalist know when resonance was taking place and what two precautions would they need to take to ensure that this is the first position of resonance? So this is a common experimental setup that you'll see where we have a fixed length of tube and then we have a signal generator so that we can vary the frequency. You may also see it with a tuning fork so that we have a fixed frequency, and then we have a tube inside another tube with water so that you can vary the length of the tube. So how would the experimentalist know that resonance was taking place? Well, we would be able to identify that by identifying when the sound is at its loudest. So as the experimentalist changes the frequency in the signal generator, the frequency will increase, so the pitch will get higher and higher, but there will come a certain point where that noise gets very loud. And when the sound is at its loudest, that's when we have resonance taking place. In other words, the air inside that air column is vibrating with a maximum amplitude at the open end of the tube. What two precautions would the experimentalist take to ensure that this is the first position of resonance? Well, that can be identified as the first time that the sound is at its loudest. So what's happening here is we have a node at the fixed end of the tube and then we have an antinode at the open end. So to make sure that we're getting the very first antinode at the open end of the tube, what we need to do is start off with the frequency at the lowest possible value. So start with the lowest frequency. And we want to increase that frequency very slowly so that we don't increase it too quickly where we would go past that position where it is at its loudest and it would be easier to miss. So we want to increase that slowly. For part C then, on a copy of the diagram shown, illustrate the mode of vibration at the second position of resonance and label all the nodes and the antinodes. So in this particular question we have the tube again with the signal generator at one end. If we have the first position of resonance, that means we have the first antinode at the open end of the tube. We're always going to have a node at the closed end of the tube. But if we want to find the second position of resonance, then we need to continue that wave pattern until we've got two antinodes. So it's the second antinode will appear at the open end of the tube. So now we want to label on all the nodes and all the antinodes. So the nodes are where the amplitude is 0, so that will be here at the closed end of the tube and again here at this point. Then our antinodes are where we have the maximum amplitude. That will be at the open end of the tube and again here. So now we're told that the tube is 30 centimeters long and the frequency of the note at the second position of resonance is 850 Hertz. We want to calculate what the wavelength of the standing wave in the tube at this second position of resonance. So I've sketched that wave pattern into the diagram above, and what we can see there is that the length of the tube is equal to 3/4 of a wavelength. We don't have a full wave in there, but we have 3/4 of a wave. So if the tube is 30 centimeters long and that is equal to 3/4 of a wavelength, well, we can just manipulate this equation so that we end up with lambda equals. So I'll bring the 4 to the other side, so we have 4 multiplied by 30 is equal to 3 lambda, and I'll need to get rid of that 3. So we have 4 times 30 divided by 3 is equal to lambda, and that gives us an answer of 40 centimetres. So that fixed tube, which has a length of 30 centimetres, shows 3/4 of a wavelength, which means the wavelength is 40 centimetres. Now, if we use that information, we can now use that to calculate the speed of the wave in the tube. And to do that, we can use V is equal to F lambda. Since we know the frequency at the second position of resonance is 850 Hz, multiply that by the wavelength, which is 40 centimetres or 0.40 metres. And that gives us an answer of 340 metres per second. And finally then, the air in the tube is now replaced with a gas, G, in which the sound travels at 1020 metres per second. So what is the frequency of the sound at the second position of resonance when the tube is filled with this gas? So we're still looking at the second position of resonance, and since our tube had a fixed length of 30 centimetres, that means that the wavelength is still going to be 40 centimetres. If we know that the speed is 1020 metres per second, then we can work out the frequency, again using V equals F lambda. So the velocity is 1020, that's equal to F multiplied by 0.4. So the frequency itself is 1020 divided by 0.4, which is equal to 2550 Hz.